Okay, we're about to start the lightning talks. Last session of the day, or actually it's more than a dozen sessions as the last session of today. So we have 13 signups for the lightning talks. I like to think of it as the record that we ever had at Haystack, as I'm the one in charge for the first time this year. So starting with a record is always good. I don't know what the previous record was, if there even was one, but I guess we're now starting that game. So I am happy to give all of our speakers exactly 5 minutes, and I will try to be very strict about the timing. And I am happy to welcome Kathleen as our first speaker. And with that, Kathleen, please take it away.
All right, thank you. All right, can you hear me? All right. So I'm here to talk about better binary quantization, or like as we call it at Elasticsearch, BBQ. This is, let's see, technical difficulties here. There we go. All right, so we are probably all familiar with quantization, and I don't have enough time to get into it. If you don't know, come find us at the dinner and we'll talk all about it. But we currently have scalar quantization at int 8, which is 4x smaller with excellent recall as the default in Elasticsearch. But we can do better. Bit quantization is a 32x space savings from float32 embeddings that directly translates into money. The problem is that when you go to bit quantization, naive bit quantization just isn't that relevant. So this is where centroids come into play. And how do we index these centroids? We use a sampling of our vectors to generate these centroids. And for each vector, this is not working. There we go. For each vector, we normalize it to a unit circle around the closest centroid. Once we get there, we will locate each normalized vector in a subspace around that centroid as it's represented by a bit vector. And then, along with the bit vector, we store a whole bunch of other data. We store the corrective offset distance from the original vector to the centroid. We store the dot product of the normalized vector, and there's also its quantized bit form. Now at query time. We run this query vector against multiple centroids, normalizing the query vector around that centroid. And when we're creating the query and we're vectorizing the query, we use int4 scalar quantization on the query vector. Now, I know I said bit quantization, so what's up with that? This is a technique called asymmetric quantization, and it works really well to generate the recall that we want. There's also some other things that we do. And remember when I was talking about corrective offsets at indexing time? That helps us get much more precise. And pre-computing the dot products instead of cosine speeds up our vector search significantly. Now, once we have the once we do this search, what we found is to get optimal recall, we do oversampling and then we rescore. And then we rescore also with the original float32 vectors, and that actually provides pretty decent quality. I've got a link here for a blog that does a lot of a deep dive explanation with a lot of math. Elasticsearch keeps it really simple to use this. It's just a mapping in the dense vector field. So super simple to start, super easy to use. And as a bonus, in 8.18 and 9.0, which we just released, it's generally available. All right, show me the numbers. What about memory requirements? So this green, I actually have a pointer here. This green column is BBQ. So when you're comparing for float32 for memory requirements, when you compare over 400 gigs for float32, goes down to 14 with BBQ. How about indexing time? Across the board, BBQ indexing was faster over a whole bunch of models than any of the other models, including int 8, int 4 quantization. Okay. What about recall? Well, it's bit quantization. There's going to be some loss of recall. However, it's not that bad, and when you add oversampling and rescore, it's actually even better. Okay. So here's some numbers from Rally, and which is our benchmarking software. Now, first of all, we've got the K, the num candidates, and then the rescore. And even with no rescore, We still get, reasonably for bit vectors, decent NDCG, although the recall does take a hit. But then when you add a decent amount of rescore, the NDCG is pretty high as well as the recall. So, performance-wise, it's a huge space savings for not that much of a recall loss. But how does it stack up against PQ? PQ's been around for over 10 years. It's similar space savings. It also achieves that 32x reduction. It also has really good recall with oversampling. So why BBQ? And it's, honestly, the numbers do not lie. It blows PQ away in terms of both quantization time and brute force search. 10 to 50 times faster quantization speeds when we're indexing, and searching is 2x or better. And it has just been merged and released in Lucene 10.2. So not only is it GA in Elasticsearch 8.18 and 9.0, it's also ready and available in Lucene. So thank you.
Exactly 5 minutes, so very good job. Next up is Christopher.
Although you can't start the timer yet, we're getting new batteries. Wait around, let me see here. All right, forward, backwards. Hey, we can drive, all right. All right, good afternoon. I'm sorry, no, that doesn't work. Let's try this again. Good afternoon. Wow, I think you guys took a bunch of sedatives. All right, so look, we got something for you here. And if the clicker, yep, here we go. It's something we're going to do today. This is going to be interesting and different. We're going to give you something informative. We're going to give you something potentially satisfying. It's actually something from the search community. Wait for it. This Bluetooth is a little slow. It's actually for the search community. What am I mumbling about? I only got 2 slides here, so let's go to the second slide. But it does require your participation, okay? So all of you that took sedatives are going to be very disappointed because you got to stand up. Otherwise, I'm just going to sit here for 5 minutes. You got to all stand up, 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 up. I want to see everybody up. All right, very good. Let's see what we have to do next. We have to wait for the clicker. Oh, we got to raise our hands. All hands up. Come on. Look at this. This is great. All right, next. Phones out. Need to get all your phones out. You all got phones. I know you got it. Come on. Nobody lost it. Nobody didn't lose it. All right, let's see what comes next. Here it comes. Waiting for Bluetooth. We're waiting for Bluetooth. Take a picture of, wait a minute, what could this be? Oh my goodness, what is that? And what does it say at the top? It says Search Community Survey. Oh my God, this is advanced technology here. Yeah. All right, so this is the way this works. In this survey, you're going to let us know your experience with search tooling. Now, why would you want to do that? Because if you do, you'll get to a last question in the survey and have a chance to let us know what your favorite breakfast pastry is. So if you don't want to have anything new and different than what you had this morning, which was just fruit and a bunch of bars, don't take the survey. However, if you do, then you're going to want to answer that question, because what's going to happen is after the survey has gone through its rotation, we'll give you the results. And tomorrow morning, if we get at least half of you to respond, your pastry, at least the one that is most popular, will actually appear. Okay? All right. All right, I'm done. Stop the watch. Look at that. I'm setting a new track record in lightning talks.
Thank you.
There you go.
Next we have John.
Hello, hello, hello. Is this thing on? Thank you, Christopher, for warming up the room. Okay, thank you, Christopher, for warming up the room. Today I'm going to talk about roaming RAG, which for this crowd, I'll say search without the engine. The idea goes back, metaphorically at least, to a point in time you guys might possibly remember the internet before Google existed. Do you remember like the Yahoo or Excite thing where you'd basically go sometimes instead of to a search engine, you actually go to a curated set of information about, what things are you interested in, click on this, fold it out. Within this category, we're trying to find someone to fix my car. You click down a few levels and maybe you get to what the answer you're looking for. It worked horribly. That's why Google did so well. But this idea might be kind of useful in this in this little scheme I'm going to show you. There are a lot of smaller documents and even smaller corpuses that are fairly well organized hierarchically like this. If I'm going to sit down and figure out why the blinker in my car doesn't work, I'm going to get the manual out that I'm unfamiliar with, and I'm going to look at the table of contents, flip it over into the section, look at the section titles, and I'm going to navigate hierarchically and roam my way down to the content that I'm actually interested in. So I threw together this blog post, and a lot of my blog posts, I try to make them kind of hands-on. We'll see if it actually works, if the demo gods are with us today. But the idea is to create a document RAG agent that is able to navigate using this concept. And basically what it is, I am using these documents called, it's kind of like robots.txt, it's LLMs.txt. And for what it is websites can choose to create this document that is a summary of everything written in Markdown in a way that is digestible by these models. What I'm doing, as opposed to using the entire document, let's see if I can actually open up the example here. Now you try the demo here for yourself. Instead of using the entire document, let's do as an example Envoyer. That's a pretty good one. You can go to this website, my demo website, choose your LLMs.txt, learn about whatever technology you want to. And normally, this document would be the full text. You could actually click on it here and see what it really looks like. For roaming RAG, I've taken a step to summarize the document where each section has like a little summary at the top. Each subsection has its own little summary, and they've all been collapsed. And so what roaming RAG can do is if you ask it a question, then the model, oh my gosh, of course I've put my paywall on this. Oh, and you've got a German keyboard. What do I do? There's no @ sign.
What did you do?
I don't know.
Hold that.
I'm holding it. John@arcturus.labs.com. That's my super secret skeleton key there.
Any longer company name?
Hey, you're the one typing. I'm not counting this as my time. .com.
That's
Let's hope it works. If it doesn't, then you'll have to imagine. Maybe it worked. All right. So I ask, what is Envoyer and what does it do with PHP deployments? And what you can see, unfortunately, I'm not streaming it back, but you can see the model think about this, and it's going to look at all these section headings. What you can't easily see here is all the section headings have like an ID. It's in a comment, so you can't see it in the HTML. But the model sees a hexadecimal identifier and the little comment that says, hey, if you want to read this section, expand it by calling the expansion tool. So it's just a RAG application with one tool called the expansion tool. And in this case, it chose to open this document called limitations. And you could just keep asking it whatever you want. It will keep randomly roaming through the document and figuring stuff out, and kind of reading the document like a human would. So it's just a toy problem, but I think it's got some fun, maybe actually practical applications when you want something easy, when you don't actually want to set up a search engine. You can just create this summary of the document and see how well it works. 5 minutes, 1 second.
Thank you. You can pass it to Phil.
Good work.
Okay.
Sweet. Cool. Okay. Hey everyone. Nice to meet you. My name is Philippe,
And yeah, I'm going to ask a question, which is, do you actually need a dedicated search engine? Which maybe is a bit of a big question for people here. But I want to talk about, obviously, Elastic, but also what you can do with existing databases. So I work on Postgres, and actually I've seen people use Postgres really, really, really far before needing to go and use a separate database or a separate search engine like Elastic. So I want to show you what it can do, and maybe how far you can stretch it while keeping your infrastructure pretty straightforward. So a little bit about who I am. I work at this company called ParadeDB. We're actually building an Elasticsearch competitor on Postgres, but most of my talk will be directly on what you can do in Postgres today outside of what we do directly. So there's 3 things you can do in Postgres full text search today. The most basic one is the like operator. The second one is tsvector and tsrank. This is the proper full text search you can do in Postgres. And then lastly, there's an extension called pgtrigram that is bundled into core Postgres, so is available on all Postgres databases out there that allows you to do some basic search engine type features. So the like operator is basically the most simple functionality Postgres gives you. The syntax is something you can see here. So if you have a query like select star from users where the name like John with an %, this will match queries like Johnny and John and Johnson and so on. It's very, very limited. It's very slow. It can basically only do what I just said, and then it has no relevancy scoring, which I know is a very big topic that we all love to think about here today. But hey, like people actually use this in productions. Most of what people do with Postgres text search is tsvector with a gin index. So this is very similar to what a standard search engine will do. So you can essentially store a tokenized representation of words. You can rank it with tf-idf, which is different than what the BM25 algorithm that I'm sure many here are familiar with is. But you can actually get quite far. It also has something called cover density, which allows you to take into account the similarity, the proximity, of words. And then you can create an inverted index on top of it, which is actually quite performant. And believe it or not, this is what the folks at Instacart use to make over $3 billion a year in revenue on their search tool. So that's actually quite impressive. And then lastly, pgtrigram, that allows you to do some basic auto-completion. So I'm sure if people here are familiar with n-grams or trigram type tokenization. So if you have a word like cheese that you want to be able to do some autocomplete on, pgtrigram allows you to do the basics of this. So you could say like, okay, if I type CHEES, for example, it's going to match with one of the trigram tokens, and then you'll be able to actually complete it with the missing E. Obviously, that's quite basic compared to the expensiveness of what all the search engines we have offer, but you can go quite far with this. It's simple, very, very simple. No pipelines, no other databases, no different languages, no denormalization. It's real time as well. You get the full transactional safety, which is a really big deal for a lot of companies. That's one of the big reasons Instacart does this, for example, and it can deal with very high update and very high write throughputs. Now, here we go, sorry. Where it doesn't do so well and where you might consider a search engine, if you need BM25 relevant scoring, so slightly more relevant results than tf-idf, which is what tsvector uses. If you want more powerful tokenizers, if you want a very complex Elasticsearch type DSL, and if you want fast analytics or fast facets, which is obviously a very big part of it, Postgres is very limited at that. So how can you do this? Well, obviously, Elasticsearch OpenSearch Solr, as everyone knows, it works very well. But one of the big caveats is you do need an ETL pipeline. What you can do, though, is you can tune Postgres super, super far. So this is what Instacart has done, for example, and they have blog posts around it that I would recommend you read if you're curious. But they actually do everything on top of Postgres and have a lot of tooling around to improve the quality of their results. And then lastly, this is a bit of a shameless plug, but I wouldn't be doing my job if I wasn't saying it. There's a new extension that exists in the Postgres ecosystem called pgsearch, which is essentially gives you the missing functionalities that I was mentioning here directly inside Postgres. And they allow you to deploy fast analytics, fast search, fast tokenization directly on Postgres so that you don't have to have an ETL pipeline. And today, this is what Instacart uses as well now, now that we exist, and it's used by IBM and a bunch of other fintech companies that we work with. This is a little bit of what it is. If you're at all curious about this, come find me at the dinner, and I'd love to tell you how we make, MVCC correct ACID compliant search possible on Postgres. Okay.
Thank you. Next up, David.
Sweet, and I'm going to do a shameless plug. If you want to hear more as well, there's a podcast episode called For the Sake of Search. If you haven't seen it, I publish it, and we had Philip from Parade on there. So, yeah, everyone should listen to it, not watch it yet. I'd love to get video. So hi, I'm David. Nice to meet you all. I am so glad that someone else did a survey first, because I'm also going to ask you to pull out your phones and take a survey. And it's not because I love making people take surveys. It's because I'm of the opinion that GitHub search is not as good as it could be. They say never meet your heroes, and I went and I met my hero, and I'm terrified. So let's talk about how I'm going about getting funding to improve search at GitHub. First, you have to quantify the pain. And this is where I'm going to ask everyone, take out your phones. You use GitHub every day, and I know you wanted search to be better. I wanted search to be better. So we had a really big pain when GitHub first started, and that pain was code search. It was a really, really, really big problem, and as a result, we built a code search engine, and the pain went away, right? No, the pain just shifted. Code search then became a much easier problem, but the pain that we still feel with Elastic's full-text search still exists. And it's not because Elasticsearch is doing a poor job. It's because we at GitHub are doing a poor job using Elasticsearch. There are a lot of people inside of GitHub who aren't search engineers building search on a daily basis. And my team, the platform search engineering team, internal tools, et cetera, we actually don't build search. We are just building the platform that search runs on at GitHub. So the first step to get funded, quantify the pain. We are going to show with this survey, hopefully, just how painful search is. Next is educate on the space. There were a lot of people internally that felt we couldn't do any better, and I disagreed wholeheartedly. We walked through with a bunch of different teams on the different spaces that we were using search, and we found all sorts of crazy things like autocomplete only using front edge n-grams, and they're like, why isn't it finding things? We're going to do regex search instead. I'm like, no, please stop. We have these cool things called trigrams, and we can build proper n-grams. So one of the biggest things is educating on the space, and thankfully GitHub has these things internally called days of learning. And this has been a platform for us to come in and say, hey, we have tools and we have ways to make this better. And also talk about relevance. And then finally, you have to cast a really specific vision. So people see this and your eyes just kind of glaze over. So this is an example of what a search looks like at GitHub. Fun fact, this is actually one of over 30 search experiences internal to GitHub. We have search on the release pages, the issue page, the PRs page, packages page. All of those are actually search experiences. The same with your project boards. Those are searches. And looking at this is fine if you're a startup, but we have gotten big and we have big indexes. You do not ever need to see 14.5 million code samples. So that involves us creating a new interface that is specific to our user, that takes away all of these very clicky things, and we should be building with relevance a single pane of search at GitHub. And that is my talk. If you haven't filled out this by now, I'm watching you. 30 more, no, I'm just kidding. Fill this out though, and thank you.
Thank you. Everyone's very good with their timing, so I am impressed. Mike, you're up.
Hello, everyone. I'm Mike. I'm with Elastic, and I'm here to talk to you today about chunk re-ranking for RAG. And just a heads up, this is some stuff that we're kind of thinking about. This is early days for this, so we're honestly interested in your feedback here. What do you think the solution would be? How it would work for you? How it would integrate for you? So the problem here is that, as we all know, RAG really operates best when an LLM is given some relevant right-sized chunks. But at least in Elasticsearch, our re-rankers right now are currently document-focused. in particular, re-rankers, they have, like with any model, they have context windows. Some re-rankers have small context windows. So, and when you're actually re-ranking a document that can be pretty large, your re-ranker can lead you astray if the answer in that you actually have the right document, but the answer that you want to feed to your LLM is farther along in the document than the context window allows. And sending whole documents to the LLMs costs a lot more money. It's pretty inefficient. And overall, this just creates an interface problem when you want to re-rank your chunks before you provide them to your LLM for RAG. And we can see this problem here in this experiment we ran. Really, what you want to focus here is in the last two columns here. This is using our text similarity re-ranker, which is document focused, and our experimental approach, where we're actually re-ranking the chunks themselves. And I can explain what's going on here. So this is the one column where we're doing on the primary retrieval phase, we're actually using the chunks to score the document. That's what you see, the 1, 2, and 3 below that. But then when you get to the re-rank phase, those chunks aren't used. And you're just re-ranking the whole document. You get some whatever order. That's the output you get. That's what you provide to the LLM, and you get the results that you saw in that table there, which here, red's bad. You don't want red. So when you re-rank, what we're looking at for the experimental approach is making this entirely chunk-centric. In your primary retrieval, instead, you just get back the list of chunks, not necessarily even attached to the docs, just the chunks. And then you pass that through to the re-ranker, who is also just looking at the chunks. And this then, what you can get out of this is a couple benefits. I mean, first off, you're sticking within the context windows that work well. Also, you can get the chunks that match your answers best, even if there are multiple chunks per document, like what you see here. So if document B really is the best answer to your query, you can get multiple chunks from that, feed that to your LLM, instead of sticking to this artificial rule of one chunk per document. So how we put all this together is we really want to create a chunk-centric solution for re-ranking for RAG in particular, but we don't have to limit it to RAG. It just might be most useful there. And as a platform, we want to allow users to customize chunk size to best fit their re-ranker, which can have a variable context window in their LLM. As a platform, you can use any LLM you want, any re-ranker you want. We want to make this something that you can configure to your needs. And we want to make it easy to get this chunk-centric view. Right now, our results, our JSON results are, they're document-centric. You can get chunks back. We use our highlighters for that, but it's in addition to your document views. We really want to flip that around, make the chunks the center of attention for some of our use cases, like RAG. And then, we want to provide an easy way to provide that into in a RAG input. Really looking more at the ecosystem. We have things like Playground, for example, where you can just plug in an index. We're automatically going to pull those chunks out. We're automatically going to feed them to an LLM, and then you can just plug in your question, plug in the index you want the answers from, and you get magical answers. But it doesn't use a re-ranker. We want to make it so you can use a re-ranker completely transparently here. And really, at the end goal of this is that we want to make chunks as the re-rank I/O modality, and make that an easy switch for all of our users. Benefits out of all of this: it's faster because you're re-ranking less information. It's cheaper because you're re-ranking less information, and it's more relevant because you're re-ranking in smaller chunks, to reuse the term, that are going to more accurately represent the information that you want to capture and pass on to further down the stream. And like I said, this is early days. We don't even we just have that experiment, but we love feedback here. This is something we want to build into our product. If you have ideas about how this would be most useful to you, we want to hear it. We're working on this actively, and we would love to hear about how could we present this to you in Elasticsearch in a way that would be best for you and your use cases.
Thank you. Pass it on to the next speaker, thanks, while I get the content ready. Froh, take it away.
Hi everyone. I'm Mike Froh. I'm here representing myself this week, so I'm going for a personal shameless plug on my own GitHub fork. I actually happen to be I believe still I'm the newest Apache Lucene committer. I was just yay! Thank you. And so I don't know what happened on my my nomination thread because I don't get to see that for obvious reasons. But I heard through the grapevine that this helped. This is a little project that I started about a year and a half ago to document kind of simple examples for getting started with Lucene. Like, part of it is because the latest edition of Lucene in Action came out 15 years ago, so it's a little bit out of date. What I did here, let me see if I can scroll. Apparently Daniel's one of the only people in the world who doesn't use the natural scrolling. And of course, I've been off my Mac for a little bit over a week, so of course, there. Okay. Command click, of course. Duh. Okay, so this is what the content looks like. It's basically worked examples with like very literate documentation beside it, where it kind of steps through, and like all of these are things that compile. You can open them in your IDE. The stuff on the left are actually just comments in the Java file, but then I use this tool called Doco to render it like this. It's I know I feel that it looks kind of like a textbook, so it's pretty easy to read. Folks tell me that they like to use this repo if they want to do a little toy something with Lucene. They'll find one of the examples I've written, modify it, fill in their own documents, and so yeah, you can also use it like that if you want. I do take requests, so this is up on GitHub, of course. There are some open issues, mostly things from me as like a to-do list. But yeah, if there's anything that you would like to learn more about in Lucene, then by all means, please open an issue. I will get a notification on my phone, and then yeah, I'll probably try to deal with it. The next thing that I'm probably going to document is Lucene's finite state transducers. Because they're yay, yeah, no, because they're one of those things where it's like I kind of vaguely get the gist, but like I don't really understand them, so it'll be a good learning opportunity for me, and hopefully I'll be able to write them up in a way that they also make sense to you. And if they don't, again, open an issue and say, hey, this example sucks, and I'll try to make it better. So yeah, that's my plug.
Excellent, thank you. So Dave's up next, yeah, just passed the microphone. So let's see if I have your slides ready to go.
Thank you. So this morning, they mentioned the lightning talks, and that occurred before Rick Hamilton spoke. And so I was like, ooh, I can do something on this. And then he did a great job talking about a lot of the ethical issues in search and AI, mainly search because we're using AI now, as opposed to just search by itself. I cut off the heretical part because I just don't have time. And my subtitle is, I am but a peon in the system. And we'll talk a little more about that. There we go. Okay. If you want to know more about my heretical thoughts, you can use the QR code. Next search, I'll tell you that I believe basically that human-augmented AI machine learning is a way to improve our search results, and that's all I'll say on that. So in general, you can't really scare me with a lot of things. I don't get upset by a lot of news and that sort of thing because I look at history and I say, well, this has happened before, or we're in a cycle and this is going to happen again. And so, when you take that long view of history, a lot of things that can be very disturbing become much more manageable. But, and I need to point it at this thing. There we go. In spite of the fact that things can be okay, I also know when we look at history, what we see is that there's a curve, and I made up this curve all by myself. use ChatGPT to render it. But the point is that historically, we see technological revolutions. And what happens with those technological revolutions is we see this exponential kind of growth in the productivity provided by some technological revolution. And when we reach kind of peak point there, we see a simultaneous, significant, horrible decrease in the health and wellness of many, many millions of people. And looking at history, I would say that we are probably heading in that direction. And at some point in the near future, we will hit a place where AI in particular is going to negatively affect a lot of people. It already is affecting a lot. Oops. Okay. We could soften this situation. You know, on the left is kind of what we're heading towards. On the right, you know, some people are still going to roll down the hill. Some people are still going to get squashed. You know, we can't make it just not be a problem. When you have a transition, when you have a movement from one kind of way of operating to another, there is destruction in that process, even as we create something new. But we could make it easier to transition. An example of softening was the GI Bill. We had millions of soldiers coming back from World War II. What are they going to do? They've been fighting. They've been executing all these military operations overseas. What they know how to do is to kill people, and we don't need them to do that back in the United States. So what do? We created the GI Bill. We provided opportunities for them to get involved in industry and to get an education that would allow them to transition peacefully and adequately. And they were the greatest generation, and they brought great prosperity and all that sort of thing to the United States, so we can be thankful for that. So that's just an example. But at the end of the day, you know, I'm a peon. I'm not a big deal. And what can I do? So, you know, up to this point, I've kind of been thinking, well, I save my pennies. And when everything, you know, kind of goes bad and I get pushed out of a job or something in a few years, I'll maybe have some money saved up and I'll be able to take care of my family and maybe help some other people out. And that one, the center one's supposed to be about treating your employee well. I generated all these on ChatGPT in a few minutes. And just the fact that I can try to take care of those that work for me and be a good example of that. But at the end of the day, I still feel pretty helpless. I want to note that we have the ears of corporate leaders for a limited time. Right now, corporate leaders actually care what we have to say. You know, we are the ones who can offer them revenue increases. And so there is an opportunity here that is very time limited. You see the clock with the 0000. That's because time is running out. And like it is for my speech. So how can we make a difference? This is just me starting to think. We can provide options for improving human replacement solutions with human augmentation. A lot of businesses just aren't thinking big enough. They're thinking, oh, I'm going to lay off these 700 people I replaced with automation, when they could improve their automation by reusing those people. So maybe we take a little more time to think about how can I help them think bigger instead of simply savings. Offer a counter narrative. Only lazy people will lose their jobs to AI. It isn't true. Maybe we can speak up and say, hey, actually, you know, this is going to affect a lot of really good people. It already is. Think about and support policies that make a difference. What does IP and compensation look like with LLMs, tax on robotics and AI? And finally, make the conversation, share ideas. You know, this is something I've been thinking about, not a ton, but a decent bit. And I was thinking about it more today. Most of my ideas probably are bad ideas. You probably have better ones. Let's talk about them. Let's share them. Let's see what we can do to soften the landing for a lot of people. Thank you.
Thank you. So next up, Paul.
Yep.
And off you go.
Off we go. And let me take a few of my valuable seconds to say thanks for that, because that's an awesome topic and obviously timely for probably everybody here and probably everybody not here. So I'm going to go ahead and struggle with the remote that seems to be going really well. And I'm going to do something that is crazy, which is I'm not talking about embeddings and vectors and things like that, because why not go a little bit off? I'm going to talk about this thing that we do with Lemur Day Labs, which you never heard of and you probably will not be able to spell. And we talk about IoT data, so data streams. And IoT data is pretty boring. It's pretty structured usually, and it doesn't have a lot of nuance to it, but it doesn't have a lot of depth to it. It's lat long, it's temperature, it's boring stuff that also makes the world work. That and large language models. So what we're going to talk about is a project that we have, MeshScope, and this is a system that consumes data from Meshtastic. And Meshtastic is an open source LoRa-based wireless network thing. This is an example of a Meshtastic device. These broadcasts, they scream out into the world, I'm right here. They're awesome, they're cheap, they're fun. And if anybody wants to ever play with them, talk to me over beer, presumably you're buying. But so we get all this data coming in, and Meshtastic is an open system. They have a public MQTT broker, so we can consume and pull in this data, evaluate data that comes in. And what we try to do with this is build a system that provides visual views of the data, AI chat, which we'll talk about just obviously briefly, outbound data streams, and MCP access. And then the design of this is relatively high level, but it's broken down too in the system blog. Super high level, one of the key things here is the box on the right, which is enrichment of this data stream. Like, we have to make this a little bit more usable and queryable and understandable by humans. So that's things like lat long means what? Okay, it's in Reno, Nevada at I don't know, I probably shouldn't know. But on the left here, we're talking about the processing architecture here, and shout out to Postgres, where the data comes in, we break it up, we enrich it, we do all this fun stuff, filtering and things, shove some stuff into Postgres, shove stuff into Iceberg for archiving and augmented search stuff later, time stream or influx for time series data, and qubit, which is our name for internal AI stuff, and then build layers stuff on top of that. So the IoT data is processed. Data retrieval is orchestrated by the LLM, not by a search engine. And so the chat stuff we'll go to for a second. What we're doing is we're providing tools and function calling, this type of stuff, to the LLM and saying, please be nice. And it might be, we'll see. Data, as I mentioned, in Postgres and stuff like that. The internal APIs that we provide the LLM cover internal and external data sources. So it can get real-time data to supplement that IoT data stream. It can do aggregates and summaries and things like that. And you can play with it. It's on our website. I'll get back to the QR code, but meshscope.lemurdatalabs.com. So everybody loves a map, and it has maps, and it has colors. So it's even better. It's like 50% better than regular map. This is basically just earlier today. I just clicked and looked at Europe. This is clicking on a particular node. This happens to be this. And it happened to locate itself here. As an interesting fact, Meshtastic will generalize your position. It basically roughens the position a little bit so that it's not a stalker thing. On the public channels, you can make private channels and share your very accurate position. Very smart. So looking at chat, I can, at the top of the site, what nodes have been active in Portugal in the last 6 hours? All right, it takes contextual data, process data, evaluated data, time-based constraint, generated response. Damn it. I am Norwegian and would like to know about nodes in my country. Please respond in the proper language. Somebody will have to tell me if that's correct, because I have no idea. All right, see? And I chose that just for you, by the way. Which node is closest to Porto? Okay, going back to Portugal. Porto is awesome, by the way, anybody planning vacations. It did a geospatial lookup. It found the nodes, it did the distance calculation, and it found the result for me. Again, this is being orchestrated by the LLM. How many nodes have been active in the last 2 days in Southern Europe? Now it's figuring out which countries constitute Southern Europe. And finally, what is the weather near Lean Card 1, which is this guy, and be expansive and dramatic about it. And so it did this wonderfully verbose, flowery prose to tell me the weather, basically here. MCP, this is cursor. I pointed cursor to our MCP endpoint in the application, and inside cursor, I just asked questions. It did the tool call, it did the endpoint call, again, without even having to go and bother yourself with our beautiful website, which you obviously should. Finally, there's a huge, like giant QR code. But we're always looking for people to engage. So feel free to go to it, contact us, talk to us, read the blogs. Don't say anything mean, obviously. But it's an interesting way to kind of turn not just search, but information retrieval and engagement around. And I'm probably over time.
Only slightly, so thanks.
For me, slightly is really good.
So, yeah, Kristian is already on his way, and you are ready to go.
Thank you. So I didn't have time to make slides. I just created this spot to let you know what we learned last year building RAG systems for billion scale, like web scale retrieval. Our first observation is we are indexing multivector. It's like we are indexing on the document level. Why are we doing that? These things belongs together as opposed to a web search where you just a human creating a query and you get a snippet back on Google, a very limited chunk of text. A model would want to get the correct segment or chunk from the document, but also the neighbors. So that's one thing. So it's much better to have them together when you're indexing it. The other observation is that we are also creating embeddings. And you will have an array of embeddings at the same size as the array of the chunks. When you're scoring these, you want to score, you're not only doing a similarity search on the embeddings, that's not enough, we know that. You need to combine it with text signals too. So the question then is, what is the combination of the similarity or the semantic score and the text score? So to evaluate that, you need to do that on the document level. So that's why we index chunks or arrays of vectors and the text chunks together. So that creates some problems. When you're indexing the web, you index a lot of weird stuff. You can also index your customer stuff. It's like the companies do that. That's how they make money. Files can be big. In some cases, we found files close to a gigabyte long. That's a long document. You can think of how many chunks that is. So when you are extracting all the information you need to combine the similarity scores and text scores together, it created a long latency. So what we see now is that we are building new features in the backend in our content nodes, so we can actually score array elements together just as we score documents. That is required for these kinds of systems. These kinds of systems are memory bound. Somebody noted that storing embeddings is costly, so you can binarize them. And you should. Still, you will be dominated by memory. So that means it's less space for the other indexes. It's like your textual indexes are huge. So what we also learned is that we are back to the 90s. You remember the stop birds? That was a thing. And people killed them. So they're back. So the problem with frequent words is that you have to read a lot of posting lists from the disks. Unless you're clever, you can use bit vectors. Still not enough. So in some cases, you have to disregard them altogether because the problem of memory bandwidth is real. When you have used all your memory for your embeddings, there is nothing left to page in your indices. So that's why we created some optimizations last month, I think, to let the weekend algorithm disregard the more common terms at given thresholds. There are more to it. So these are the things we didn't think we would work on 6 months ago, but the big RAG systems told us that it's important. Other things we learned is that creating, you have to stop me. Okay, yeah, there are so many things, but we have beer later. So yeah, over there we can talk about what this means when you're building HNSW indexes for these kinds of systems and how you have to partition them to make this viable, actually. Okay, I'll stop there. We'll continue over there. Thank you, guys.
You. Thanks. So, passing the microphone.
Yeah, now we
Let's
gotta
see.
pass the mic.
Yep. And agentic query understanding. Chuck.
Awesome.
You're
Thank
on.
you. Hello, everyone. My name's Chuck Meyer. I work at Algolia, but I work in DevRel, so you're not going to get anything useful today, unfortunately. So today I want to talk a little bit about agentic query understanding using MPCs. MPCs just came up in Paul's talk. If you're not familiar, first there were the models, then we get agentic models, and then we started to teach them how to use tools. Last November, Anthropic said, what if we kind of define structure around that? So they proposed the model context protocol. It's kind of been accepted across the board at this point, so a lot of models have been trained and are now aware of being able to define MCPs. They describe it as USB, right, for your agentic model. So basically, it provides an abstraction layer. And by the way, this entire lightning talk didn't exist 90 minutes ago. This came out of a conversation I had with Matt Overstreet when we were talking about like wrapping up tools and models and things like that, and the fact that everything kind of hinges on those descriptions, right, and allowing the model to understand how to interact with your API or your code using this description as an abstraction layer. And so that's where we kind of read about it, thought it was interesting. And the cool thing that Algolia had going for us is we already have all of our APIs described as open API specs. And we actually generate SDKs from those specs. So it was super easy for us to just generate an MPC and just start goofing around with it and see what we could do. So this is what our MPC looks like. We essentially took all of our endpoints, came up with descriptions based on the descriptions that were in the Open API spec, and just kind of put it all in. This is all generated in Node. We also have a Go version of it. And then basically all I have to do is I go into Claude, and I go into the desktop config. You have to use the desktop version for MPCs right now. And I put all this in. That's a read API key, so you can take it and play with it if you want. That's fine. We don't mind. But basically, so I told Claude, hey, Claude, you've got this fashion index. Now you know about this fashion index. And then I just said, okay, Claude, let's see what we can do. And hopefully the demo gods are with me. So again, this is a recording of it because you got to run it locally. But I said, hey, Claude, I'm on my way to Paris. And, I'd like to pick out, ooh, this is going real slow. But I'm on my way to Paris, and would you be willing to help me out with some outfits for that trip? Because I'm not very fashionable, and I know people in Paris often are. And so then Claude goes and responds, thinks about it for a minute, and says, yeah, I can help you with that. Can I get access to that index? And I say, yeah, sure. So now Claude's going out, and it's actually querying against the index directly. Now, the queries it's making are pretty kind of dumb and straightforward, men's fashion, things like that. But it's taking that information, and now it's going and it's actually providing me with some outfits based on that query response. And then I can kind of go back in and say, oh, that's pretty cool. So it's giving me a couple different ideas, indoor, outdoor look, and some tips and tricks because, of course, it's an LLM and it knows some other stuff. And I can say, yeah, well, that's cool, but I'm actually going to a meeting. So can you actually give me an outfit that's, very specific to going to a business meeting? And Claude, it's not going to do another query because it's already got a bunch of information. It's going to take all of those results that it got back last time and it's going to combine those together to get me an outfit. So that's kind of a fun little kind of brute force way to kind of play with this from the query side. And I thought that was kind of interesting and fun. And let's see, how do you get past the video now? There we go. But where it gets really interesting is we gave it all of our backend admin APIs as well. So listing indices, pulling configuration, adding rules, all of that stuff. And so we've already started kind of playing with that side of it and doing things like, hey, Claude, why was that result third? What rules came into play? And what could I do to improve relevance on that particular record? Hey, Claude, can you enrich my records? Nick Vilko, my boss, was playing around with generating a index of science fiction novels and things like that. and was like, hey, Claude, can you actually tell me all the ones that won Newbery Awards and add an attribute for that and facet it? And Claude did. So we're playing with adding like a Clippy type chat configuration for our dashboard. So literally you can ask the dashboard about, hey, tell me some stuff about my index and help me with the configuration of it. And that's kind of where we're going next. This is a public. This is, again, specifically for Algolia. This is our node-based MCP. If you want to pull it down and play with it, you can reach out to me if you want the credentials to get that fashion index just to kind of goof with it. But we're just early days on this. We really literally have been playing with it for 2 weeks. So we're kind of excited to see where it goes next. Thank you.
Thank you. So Trey's up next.
Thank you much.
And?
All right, we'll get going. Hi, everyone. Trey Grainger, lead author of the AI-powered search book, along with Doug and Max Irwin. Yeah, this is the conference app from earlier if you want. Just a note, this is part of the AI-powered search community, so we created an online community around the book. I'm not here to talk about that today, but if you've joined this, you can continue discussing and seeing lots of cool stuff there. So I'm going to talk very quickly about quantization, design patterns, key metrics, and why you should care. So I did a workshop yesterday, and there were some questions that came up around quantization and how it's used. So I just thought, following up on the BBQ talk from Kathleen, I would maybe zoom out a little bit and talk about how quantization is leveraged. So very high level, if you're not familiar, quantization is a technique used to reduce the memory footprint and computational complexity of numeric data representations like embedding vectors. In the context of embeddings and search, quantization involves compressing them by reducing the number of bits used to represent the features of a vector. So very conceptually, if I took a picture of the cover of the book with no quantization, sort of map this out as features. Think of like each of the pixels as features. If I use scalar quantization, it's basically just reducing the precision. So you can see this kind of represented by this somewhat muted color scheme in the middle, and then binary quantization is every pixel is going to be represented as a 0 or a 1. So in this case, you can still mostly make out what the book is, though not perfectly, but it's still kind of sort of good. Quantization can be applied both to embeddings, which is what we usually talk about at search conferences, but also to the models themselves, to LLMs, in terms of how they internally represent data. So I've got a nice expensive Mac Studio M3 with 512 gigs of RAM at home, so that I can run basically any model. But even the large DeepSeek models have to quantize to 3 or 4 bits just to get them to run, but I can run them. When you do that, this is a graph here of perplexity. So there's a lot, you can't see the bottom of the screen, but there's a lot of different things you care about when you're quantizing LLMs. So perplexity is one, which is the degree of uncertainty a model has in predicting tokens. So high is bad over here. So if I've got 2 bits or 3-bit quantization, you see a lot of perplexity and uncertainty. Whereas if you have full precision, the model performs much better. It's much more predictable. But there's other things with LLMs, as you can imagine, like time to first token, inter-token latency, end-to-end latency, and overall throughput that you really are trying to optimize for when you're using quantized versions of the models. But for search specifically, we're usually trying to optimize memory usage and or speed of queries relative to the amount of recall we get back. So for example, if you take a full float 32 embedding and you quantize it to an int 8, so you're going from 32 bits to 8 bits, you've reduced 75%. You've got a 75% improvement in terms of the amount of memory and space required. And when you do that, you can still get basically about 90 to 93% recall, at least on the data set that I'm using. The interesting thing, though, is even though you lose recall, if you over-request, as Kathleen mentioned earlier, and then rescore based upon over-requesting, you can get back up, depending on the data set, much closer to 100% recall. So that's a way to get a performance optimization without having to fully utilize all that memory. And so there's a bunch of complementary techniques that go along with quantization. Sorry, you can't see the bottom, but these can all be used together, and in fact, often you will use at least 3 of the 4 together. So these techniques are ANN, approximate nearest neighbors search, and this is a search to filter the number of documents that must be scored. to a smaller subset that are likely to score well. So usually we do this with HNSW, for example. You initially filter down the results you're going to look at, and you don't do a vector comparison across every pair of every document with the query. But there's IVF and there's other mechanisms for doing this. So that's something you want to do to optimize your upfront querying so you have less calculations. Quantization then allows you, for each calculation, to do less work because each feature is using less memory. And then there's things like Matryoshka representation learning, which allows you to just use less of the embedding when you're searching to find your initial set of search results. And then there's re-ranking. And re-ranking just comes into effect at the very end. And this is when, after I've done my initial search and scoring with my quantized versions of vectors, I just over request because I may not have the best results at the top, but I should still have the best results pretty close to the top, if I go out to 100 or 1,000, so I just re-rank those. So in general, scalar quantization, going down to int 8, you save about 75% of the memory, you get about 92% recall. If I use binary and go down to a single bit for each feature, I can get about a 96-97% improvement. And my recall isn't great. It goes down to about 60%. But if I over request substantially, I can still rescore and get back closer to 100%. There's product quantization, which I won't talk about for time, but you can actually go further beyond binary quantization and get even more space savings. But again, you've got this issue of losing more recall, and but you can get back up there with re-ranking. And I'm not going to talk about Matryoshka, you can look that up. But last slide here, you often will combine these together. So this is a code example from the AI-powered search book where we're actually doing ANN, we're doing IVF, we're doing Matryoshka representation learning, and we're doing binary quantization, and then we're doing re-ranking. And I'm getting a 99% improvement in search speed, a 98.2% reduction in memory and index size, and my re-ranked recall is about 72%, which isn't great, but considering I'm only using 1% of the original index size, that's not bad. So anyway, so if you can look at, I'm Trey, join the community, buy the book, come tomorrow morning to get the book signed, and come chat with me tonight at dinner. Thanks.
Thanks. So, next up, Daniel, stage is yours.
Thank you very much. I think I'll just use very good. I'll use the keyboard because I have many slides. So I think your brain is completely full. I think there is nothing else I can put in there, but that will not stop me from trying. Basically, the title of the talk just tells you everything. So, metadata-aware vector embeddings, where the model is basically a mixture of experts. That's what we do. If you have been thinking about ways to inject other signals besides, text embeddings into your vectors, then this is the way to do it. Superlinked was mentioned on one of the slides we saw previously. under the glimmers of hope, so that's good. So yeah, you have those two separate systems, and obviously, in big tech, the way we build vector search systems is we have custom encoders that feature engineer all our observations about the given entity, and then we make an encoder that encodes all of those signals, right? Like if you went to the TikTok recommenders team and told them that, hey, you can hybrid search your, structured, you can do boosts and all of that stuff, that obviously wouldn't fly, right? And our goal is to help you integrate those two worlds, the structured data and the unstructured. I don't have to tell you what embeddings are, but basically, what if your data is not just text, because it isn't, right? So you have some object with some rating and description. Wouldn't it be cool to have some way to make vectors that somehow encode the numbers, let's say, and the text in a way that is kind of reasonable? So not by stringifying the number and encoding it with a language encoder that treats it as text tokens. If you try to do that, this is a very simple experiment you can all replicate. just take 100 integers, 1 to 100, stringify them, make embeddings, and plot them, and just understand how the latent representation in a text encoder looks like for numbers. It's basically noise. And then obviously it only goes bad from there because you have objects with tens of properties, and those properties are location and numbers and lists of IDs and all of that, right? So how do we go from something like this to embedding? And why do we want to do it? Because when you have a query like this, family-friendly hotels near Manhattan Midtown, like, wouldn't it be awesome if you could take that query and make an embedding out of it that kind of asks for family-friendly things and hotels and things near Manhattan Midtown, all encoded in the embedding itself, right? Without the extra treatment. And then what about, like, we can inject all kinds of biases in there. There can be context of the user, right? Where is the user located and which hotels they booked before, right? Like, imagine you have some way to take all of this and make an embedding out of it that encodes all of that stuff. And the question is why? Okay, so when you work on a search system, basically we're running like a multi-year optimization over the space of potential query JSONs in your open search system, and you have all these like tricks and things you are using to search this space of queries that you are hoping to encode with that JSON query, right? And it's actually kind of hard to optimize over JSON space of JSON objects, right? This is not smooth. This is not what like ML people like to do. And so wouldn't it be better if somehow you could make a user vector that encodes everything you know about the user, make a query vector that encodes all those biases in the query. Okay, this is my other query, but similar idea. And then you can kind of just pull that query closer to the user. Okay, that's search personalization. And then you can look up your hotels or whatever it is in that same space. Like, this is then what you are optimizing over, right? Much more straightforward. We have an open source product that helps you do this stuff. It feels like building some stuff in Python. And basically what this does, I mean, the way this fits in your stack is you have your data and your use cases, and then we have encoders for different kinds of, I don't want to say modalities, because then people think text and images. We have all kinds of other stuff. And then we sit on top of a vector database. So we work with Redis, Mongo, and Quadrant. We are adding more. I just got a text that we spun up with the customer, another like a 2 terabyte Redis instance today. So I'm looking forward to that bill. And I mean, I added this slide just for you. I don't show this anywhere else. You are all very nerdy, so I added this one. Just basically like, we have a sponsored dinner tomorrow, and I will not be able to explain this right now. So basically my call to action is come to our dinner and let's chat. But basically we have like a DAG object we create that contains both this idea of encoding all kinds of signals into the vector and then aggregating that vector with other vectors and eventually coming up with a search object that then we use to search in the underlying vector index in the database. Lots of use cases, obviously. We have some resources. We have a table that compares 47 different vector databases on maybe like 40 different features. This is open source, and more. And basically, choose your own adventure. I have 3 QR codes. I have the most QR codes per slide. Okay, and the 3 options are dinner for tomorrow, these slides, so there is like self-referential element, and then our GitHub, where basically kind of a lot of what I described is available, Apache 2.0, go check it out. And then we have a private preview cloud product if you want to scale it to like those 2 terabyte Redis instances. Thank you.
Thank you. So, with the winner of QR codes per slides, we conclude the lightning talk sessions. So let's give all of our speakers a round of applause. And being a German, and we are perfectly well on time, that pleases my not only inner German, but my real German. So thank you very much for the speakers being on time, for the audience, for your warm rounds of applause. That concludes day 1. We are now all meeting at Cardinal Hall. Please don't forget your name tags that I am not wearing right now, but you are all, because that will give you some vouchers for drinks and, well, entrance to the tent, I think, where food is served. So have fun tonight. See you there, and see you tomorrow for day 2. Thank you.